It is time for another Hamiltonian mechanics problem. I want to do this one, and again, that this may not be the best method to solve this problem. Lagrangian would probably be better, but I want to do it to practice Hamiltonian, and we have 2 degrees of freedom. And this is a problem straight from the textbook. I'm using Taylor Mechanics, and this is chapter 13, number 13. So 13.13 if you want to look at it. I don't normally do that, but I like to make up my own problems. So here's the problem. A mass, m, is confined on the surface of a cylinder of radius r. So it has to be on the surface. I don't think it can go up here in the end caps. And it's subjected to a force, negative k. Oh. I've got a lot of little scratch outs right here. The force, F, is negative k r hat. So it's in the r hat direction. Okay. Now, I should have, let's put that as, I just realized you used r twice. It doesn't matter. It's fine. Okay. So we want to use Hamiltonian mechanics. To do that, the goal is to pick degrees of freedom. In this case, we should have, 2, right? We're going to use cylindrical coordinates. The object can move in the z direction, and it can move in the theta direction. So that's 2 degrees of freedom. It cannot move. It's constrained to move on the cylinder, so it can't change r direction. When we do that, I can write down the Lagrangian. I need to do that. To do that, I'm going to have to find the potential. I'm going to do that. Then I can write down the Hamiltonian. Actually, I can't. I need to calculate the momentum, which isn't always obvious. You should always do this based on the Lagrangian. I can find the momentum. I'm going to get 2 momentums. I'm going to get a pz momentum and a p theta momentum. So I'm calling the angle in the xy plane the polar coordinates theta. I know people use phi. I don't know. I grew up with theta. I'm sticking with theta. If you got a problem with theta, take it up with theta. I apologize. Once I find the momentums, then I can find the Hamiltonian as the sum. This will be pz times z dot minus the Lagrangian, and then plus p theta dot minus the Lagrangian, all those 2 together. And remember, we're using this dot notation. Z dot is the derivative of z with respect to t. There's a bunch of great stuff here, and I'm gonna model this. I'm gonna calculate this, and I'm gonna model. I'm gonna make this in Python. I don't know if it's gonna work, but I'm gonna do it. So the first thing we need to do is define the potential. So remember that potential is defined as negative the integral of f dot dr, where dr is the displacement vector. Now, if this is a conservative force, which it has to be if I want to make a potential, I'm not going to check that, but I'm just going to assume it, then I can integrate this path over any direction. So let's integrate along the actual r hat direction. That means that the potential is going to be a negative, so positive, of f k r dr. So, and then plus a constant, but we don't care about constants, we only care about potential. So this gives the potential is only going to depend on r, and it's going to be k r squared. Now, this is my r value right there. And so notice that this depends on the radius of the circle, capital R, and z. So if I have this triangle right here in any particular shape, then r squared is going to be r squared plus z squared. So the potential is actually, there's a 1/2. Man, I'm doing bad today. 1/2, when I integrated that, 1/2 k r squared plus z squared. So I have the potential, now I need the kinetic energy. So the kinetic energy, whenever you're not sure how to write it, you should write it in terms of Cartesian coordinates. So let's write the kinetic energy as 1/2 m x dot squared plus y. I should just start over sometimes. Y dot squared plus z dot squared. I'm thinking ahead. And then if I can get my variables in terms of, or my x's in terms, and y and z's in terms of my other variables, I can figure these out. I already know z is z, so I don't need to worry about that. And then if I'm looking at this from the top, here's x, y, this is r, and that's theta, then I can say x is r cosine theta, y is r sine theta. So let's take the derivative of these with respect to time. It's pretty easy. x dot is going to be, the only thing that changes with time is theta. So this is going to be negative r sine theta, theta dot. Y dot is going to be equal to r cosine theta, theta dot. Now, if I square these and add them together, that's pretty easy, right? I can get this. X dot squared plus y dot squared is going to be equal to r squared, theta dot squared, sine squared theta, plus r squared, theta dot squared, cosine squared theta. And then I can factor out the r squared, theta dot squared, and I get sine squared plus cosine squared. So this is just r squared plus theta dot squared. So the kinetic energy is 1/2 m r squared, theta dot squared, plus z dot squared. Okay, now we can write down our Lagrangian. And we need that to find the potential. So let's write down the Lagrangian. L equals t minus u. So that's going to be 1/2 m. I'm going to put these in two different terms. R squared, theta dot squared, plus 1/2 m z dot squared, minus the potential, which is this. So minus 1/2 k r squared plus z squared. Now that I have my Lagrangian, I can find my two momentums. So pz is going to be equal to the partial of L with respect to z dot. So if I take the partial of this respect to z dot, there's only one term, it's right here. So the partial of this respect to z dot is just going to be m z dot. So the 2 comes down, that cancels. And that's, I mean, the momentum is mass times velocity, z is the velocity, that makes sense. P theta is going to be the partial of L with respect to theta dot. So over here, there's only one theta dot. It's right there. That use the power rule. The 2 comes down, 2/2. I get m r squared theta dot. So that one, you could, that is the angular momentum, right? But if you didn't see that, that's fine. Now I can write the Hamiltonian. I have my p and my z. I can write my Hamiltonian. So the Hamiltonian h, let's just write it out. It's going to be pz z dot dot. Yeah, blanked out there. Z dot plus p theta, theta dot, minus L. And so this whole thing is L. 1/2 m r squared theta dot squared minus 1/2 m z dot squared plus, because minus a negative, 1/2 k r squared plus z squared. Okay, now I want to get my Hamiltonian in terms of p's and q's. Mind your p's and q's, that's where that comes from. That's not true, but it's still fun to say. And so I have a z dot and I have a theta dot, z dot. I don't want those. I need to get rid of those. So I can use up here these definitions to solve for the dots, right? So from this, I get z dot is equal to pz over m. Theta dot is equal to p theta over m r squared. So if I put those in, I get h equals pz over m plus p theta, theta dot is this, p theta over m r squared, minus 1/2 m r squared, theta dot squared is this squared, so I get p theta squared over m squared r to the 4th, minus 1/2 m z dot squared is going to be p z squared over m squared. And then I have the kinetic energy of the potential, 1/2 k r squared plus z squared. Now it's all in terms of p's and q's. That's a q. All right. So here I have pz squared over m. And here I have negative pz squared over 2m, because this cancels that. So I can add these two together and I get pz squared over 2m, which you knew that. You knew the kinetic energy, that's going to be coming up. Same thing over here. I have p theta squared over mr squared minus, this is going to be cancel 2, cancel, cancel. And so I get plus p theta squared over 2mr squared. And then I have my potential. Plus 1/2 k r squared plus z squared. So that is the total energy. That's the kinetic energy in the z direction, kinetic energy in the theta direction, the angular kinetic energy, rotational, and that's the spring potential energy. So that's my Hamiltonian. And it only has pz's, p thetas, z's, and theta, with theta doesn't show up actually. Okay, let's write that down so we can start a new sheet. H equals pz squared over 2m plus p theta squared over 2mr squared plus 1/2 k r squared plus z squared. Now I want to use the Hamiltonian, so let's do this in the z direction first. So I'm going to say, from the Hamiltonian equations, I get two first-order differential equations. The first one says that z dot is the partial of h with respect to pz. So let's do that. So z dot is going to be the partial of h with respect to pz. There's only one pz term, it's right here. So I bring down the 2, and I get pz over m. And I'll just write it over here, equals z dot, which is exactly what we had before. Okay, so that's not actually that useful. The other equation, pz dot, is equal to negative the partial of h with respect to z. And so there's only one term with z in it. It's right there. I have 1/2 k z squared. So I'm going to get negative k z. So the 2 comes down. There's a negative sign that's that. And that's equal to p z dot. Okay, so now I have two equations for z. Now let's do them for theta. So theta dot is going to be the partial of h with respect to p theta. So there's only one p theta. It's right here. And so I bring down the 2. I get p theta over, that's a p sub theta. P theta over m r squared equals theta dot. Again, that's the same thing I had before. Now, p theta dot is negative the partial of h with respect to theta. But wait, there's no thetas here, right? So the partial of this with respect to theta is 0. So p theta dot is 0. That's it. We're done. Now, we want to model this, and this one you probably could calculate by integrating, but we're not going to do that. Instead, we're going to make a numerical model, because I want to make a visual model of this. And so my light's a little off. So what we're going to do is to start with p theta and pz dot and p theta dot. So if I break this into delta t is 0.01 seconds, I can assume that pz dot is constant. If pz dot is constant, that's going to be delta pz over delta t. So it's pz2 minus pz1 over delta t, right? That's my that's pz2 at the end of the time interval. That's at the beginning of the time interval. So this is going to be, that's not equal to. So I get pz2 is pz1 plus pz dot delta t. So I can calculate pz dot right here. I can use that to update the momentum for pz. Now let's jump down and do the theta one next. So p theta dot equals 0. And so if you do the same thing, we see that p theta 2 equals p theta 1 plus 0 delta t. So p theta is constant. It doesn't change, right? Because the derivatives, which we knew, which is fine. Now let's jump over and do the z and the theta dot. So now I'm going to assume that pz2 is constant. So I can calculate z dot, and then I can say z dot is delta z over delta t. So from this I get z2 equals z1 plus z dot delta t. And remember, I calculate z dot with my momentum. And I can do the same thing for theta. theta dot is delta theta over delta t. So theta 2, theta 1 plus theta dot delta t, which theta dot's constant, right? Because p theta is constant, and that's that. So we're going to do this and break it into steps. So we need to do this numerically. We need some numbers. So let's pick some numbers. I'm going to say r equals 0.1. I'm just picturing in my mind a cylinder, like that big. Now I need initial values for p, z. I need initial values for z. So let's say z equals the initial value for z. This is all at t equals 0. Z equals 0.03. I just picked that. I just picked it. Pz equals 0. Okay, it's not moving up or down. Theta equals 0. Theta, p theta, is going to be equal to, let's say, I do want to give this a value, otherwise it's going to move up and down. So let's say 2 pi, 4 pi radians per second divided by the mass, which I do need the mass, of 0.1. So 4 pi over mr squared. Let's pick that. Okay, let's make this happen in Python. I'm going to make a visual model of this just for fun, because I can. Okay, so let's jump over here to Python. So I'm using GlowScript Web v Python. Make this bigger. So I'm going to start off with my constant. There's no gravity in this problem. Oh, I didn't pick k. 3. K equals 3. R equals 0.1. Z equals 0.03. I'm looking over here. M equals 0.1. If we need to change the values, we change the values. Theta equals 0. Pz equals 0. P theta equals 4 times pi divided by m times r squared. I don't know, maybe it doesn't work. We should make it a little bit bigger. And then t equals 0, dt equals 0.01. Okay, so the first thing, I could just make a graph, but like I said, I'm not going to do that. I just don't want to. I'm going to make a cylinder. So let's make our cylinder, what should we call it? Let's call it a drum. I want to give it a name. So drum equals a cylinder. The position is going to be, I need to say how long it is. I know the radius, but I need to know how long it is. Let's say if it's 0.1, let's say it's 0.2 tall. Yeah, let's just try that. So the cylinder object starts at a location, and then you have a vector going to the other side. So I'm going to say the position is equal to, let's give this h. H equals 0.2. So the position is going to be vector 0, 0, negative h over 2. The radius is r. I'm just going to run it just so we can see what that cylinder looks like. Oh, I didn't give the axis. Axis equals vector 0, 0, h. Yeah, this is the z direction in Python, in and out of the paper. And so it looks like a circle, but it's not. See, it's got some dimensions. Here's my thing. Okay. Now, I want to be able to see. So what we're going to do is actually make the cylinder see-through. So I can just say opacity equals 0.3. Isn't that nice? Let's put, should we put the origin? Yes, let's do. So let's put, I'm going to say origin equals sphere. Position equals vector 0, 0, 0. Radius equals 0.002. Color equals color dot red. Let's see if that's big enough. Yeah, that's too big. Okay, I'm glad I ran it. So let's say 0, 3. I'm just picking stuff here. a little too small. 7. Okay, that's good. There's my center. Now I'm going to make the mass. So to do that, I'm actually going to calculate R and Y. I mean X and Y. So X is R times cosine theta. I have a value for theta. Y equals R times sine theta. And then I can plot. I can make my mass. Let's call it a ball. Ball equals sphere. Position equals vector X, Y, Z. So I have Z values, I have X, Y, I have everything. And then the radius, let's make it the same. Let's make it a little bit bigger. 0.009. Color equals color.yellow. Make trail equals true. Run that. See what it looks like. Okay. So it's on the sphere. That looks pretty good. And a little big, but who cares? Okie dokie. Now we're ready to go. Let's say while t is less than 5. I'm going to run it for 5 seconds. And I'm going to say rate 100. So rate 100 says don't do more than 100 calculations every second. Since I have a time step of 0.01, that will make it run in real time. The first thing I'm going to do, looking at my calculation over here, is to calculate pz dot. So I'm looking at my Hamiltonian equations and I have that. Pz dot, I'm going to write it just like that, is equal to negative k times z. I have a value for k, I have a value for z. Now I can use pz dot to update pz. I do have a pz. So pz equals pz plus pz dot times dt. Now let's do the same thing for theta. So p theta dot 0. Let's just say it. I'm going to write it down. P theta dot equals 0. Then I can say p theta equals p theta plus p theta dot times dt. And this is a dumb step because p theta doesn't change, right? But that's fine. It doesn't matter. It's still going to calculate it just for fun, just to be full, right? I'm making sure I have a p theta right there. Okay. I should save this. I never saved it. Save. Let's call this Taylor Chapter 13, number 13. I'll never find this ever again because I won't remember to search for that. But maybe I will. Did it save? It's saving. Save. Okay, it's saved. Now I'm going to update z. So I'm going to say that z dot is equal to pz divided by m. That's from my Hamiltonian equation. And now I can use that to update z. Z equals z plus z dot times dt. Now let's do the same thing for theta. Theta dot is going to be equal from Hamiltonian equations. P theta divided by m times r squared. Now I can update theta. Theta equals theta plus theta dot times dt. And then t equals t plus dt. Now, the other thing I need to do is to move my ball, right? I change the x, y, and z values. I change r, I change theta and z. So let's move that. So I'm going to say x, I'm just going to do the same thing. R times cosine theta. Theta changed. Y equals r times sine theta. Z is z. So I'm going to move the position of the ball. Ball.pos equals vector xyz. I think that should work. Let's see what happens. I'm kind of excited. It's just falling. It's just oscillating up and down. Oh, it is moving. Let's give it a larger p theta. Let's make this 14. So it has p theta. It's not moving though. Theta is not changing. Theta equals theta dot plus p theta. P theta. Okay, let's make that even bigger. I don't know what I'm doing here. Why is it not moving? I'm kind of disappointed here. It is moving up and down, but it's not rotating. So let's just print p theta. Let's print theta dot, which is p theta divided by m times r squared. Oh, that's why. Let's just give it a value of 10. There. Okay, now it's working. 1. Nope, too much. 0.1. Nope, too much. I went from one extreme to the other. There we go. Nice. Look at that. So the angular momentum is just constant, right? So the promotion around there is going to be constant. And that didn't seem like 5 seconds, but I'm pretty happy. I'm pretty happy. That's it. That's it. That's the code. And it looks cool. Okay, let's save that. And we're done. I'll post a link to this code down below. If you want to play with it, you should. And I'll talk to you later.